You have a 9.6 mole pure sample of an unknown material. After 5.6 hours, you discover that 80% has decayed. Determine the half-life, decay constant, mean life, and initial decay rate. Also determine what the decay rate is at 5.6 hours. Okay, so I want to go over this problem, even though this is just exponential decay, and we've already dealt with exponential decay in RC circuits and LR circuits. Still want to go over this because this involves the half-life, and that's something we haven't talked about before. So, although we could use our more familiar exponential function, I want to use the half-life function here, the half-life, not the half-life function, but the half-life equation, just to show how you would solve using this. So first off, we're told that 80% has decayed. That means only 20% remains. So this in here is really 0.2 in naught. Only 20% remains. It's going to equal in naught times 2 to the negative t over my half-life. So the in naughts are going to cancel. And I'm going to have 0.2 equals 2 to the negative t over the half-life. What I'm going to do now is take the reciprocal of both sides. So if I take the reciprocal of both sides, this becomes 1 divided by 0.2 is just 5. And this just becomes 2 to the positive t over the half-life. You don't have to do this step. This is a personal preference. It just gets rid of the minus sign. Now take the natural log of both sides. So this is the natural log of 5. And this becomes t over the half-life times the natural log of 2. When you take the natural log of a function, you have to go through the, whatever the rule is called, chain rule, natural log rule, whatever it's called. But the point is the power, the exponent, gets brought down in front, and then you take the natural log of the number. If this was an exponential, the natural log of the exponential function is just 1. Otherwise, you have to leave it as the natural log of whatever your number is. Okay, so now solve for the half-life. So I've got t to the 1/2 equals t times the natural log of 2 over the natural log of 5. Okay, now I can put in my time. So for me, that time is 5.6 hours, and I can leave it as hours. Don't have to convert it. It's fine to convert it, but I don't have to. And then do the calculations, and I get 2.41, we'll say 18 hours. That's the half-life right there. Okay, now that I know the half-life, it's really easy to get everything else that I need. Well, most everything else. So for example, to get the decay constant, so lambda there, to get the decay constant, we have the relationship that lambda times the half-life is just equal to the natural log of 2. Okay, so that's easy enough to do. I also have the relationship that the half-life is equal to tau times the natural log of 2. So I can make use of that to get the mean life. Remember, that's what tau is. Tau is the mean life. To get R naught, so that's the initial decay rate. Well, we've got this wonderful formula. R naught equals N naught times the decay constant. So can figure that out. Notice the hours here, the units here, decays per hour, and the units for the decay constant are in inverse hours. So the point being, I said earlier, you could convert the half-life to seconds if you wanted to. You could convert this 5.6 hours, but there's really no need. I don't recommend it because these other units are going to be in whatever units this is here. The last thing is R. I need to get the decay rate at 5.6 hours. Well, we've got the formula for that. R equals R naught, and you can leave it as e to the negative t over tau. Or if you prefer, you could do R naught equals e to the negative lambda times t. Okay. Or if you prefer, R naught times 2 to the negative t over the half-life. It's really whatever you prefer. All of these within rounding will give you the same answer.